We'll start in 1 minute. Today we'll start in Chapter 6, Section 6.1. This is the section on the greatest common factor and factoring by grouping. Yesterday we reviewed multiplying polynomials, and now we're going to start talking about factoring. Factoring is just the reverse process of multiplying, and we can always check our factoring by multiplying. Okay, the greatest common factor, or GCF, of two or more terms is the largest expression that is a factor of all the terms. So in this first exercise, find the greatest common factor of the following pairs of positive integers. 14 and 35. Well, listing the positive integer factors of 14 is not very hard. I'll do that down here. One is a factor of everything. 2 is a factor, 7 is a factor, and 14 is also a factor. Those are the only positive integer factors of 14. The positive integer factors of 35 are 1, 5, 7, and 35. So the greatest common factor is the largest factor of both numbers. So 1 is a factor of both, but 7 is also a factor, and it looks like 7 is the largest or the greatest common factor. So sometimes you'll see this notation, the GCF, or the greatest common factor of 14 and 35 is 7. Okay, the next pair, 13 and 21. What's the greatest common factor of 13 and 21? So I'll give you a chance to answer that. Should take less than 2 seconds.
1.
Yeah, 1. 1 is the greatest common factor. The only integer factors of 13 are 1 and 13. The integer factors of 21 are 1, 3, 7, and 21. So 1 is a common factor, and it's the only common factor. Consequently, it's the greatest common factor. So the greatest common factor of 13 and 21 is 1. Okay, the next pair, 24 and 60. What's the greatest common factor of 24 and 60? Well, another technique for finding the greatest common factor, if you can find the prime factorizations of the integers, then you can identify the greatest common factor by looking at the prime factorizations. So every positive integer greater than 1 has a prime factorization, a unique prime factorization. So 24, the prime factorization of 24 is 2 times 2 times 2 times 3. Right, 8 times 3 is 24. This is called the prime factorization. The prime factorization of 60 is 2 times 2 times 3 times 5. That's like 4 times 15. So that's the prime factorization of 60. So the greatest common factor can be found by identifying the common prime factors. Both 24 and 60 have 2 factors of 2. Even though 24 has 3 factors of 2, 60 only has 2 factors of 2. So the common prime factors are 2 times 2. Do you see that? Is there anything else common besides 2 factors of 2? Yeah, 1 factor of 3. 1 factor of 3 is common to both. And that's it. And then you just multiply the common prime factors. 2 times 2 times 3 is 12. So the greatest common factor of 24 and 60 is 12. Hey, then the greatest common factor of 17 and 51. Well, 17 is a prime number already. So the prime factorization of 17 is 17. 1 is not considered a prime number, but we do include 1 when we're finding greatest common factors. The prime factorization of 51 is 3 times 17. So the greatest common factor of 17 and 51 is 17. Okay, there's a question on YouTube about how to find the prime factorization. I'll just do an example using the number 60, and I'll construct a prime factorization tree. 2 is the smallest prime number, and 2 is a factor of 60. So we can write this as 2 times 30. And 2 is also a factor of 30. So in the next branch, we bring down this 2 and then write 30 as 2 times 15. So 2 and 2 are prime numbers. 15 is not a prime number, so the next one, 2 times 2, and then 15 is 3 times 5. And 2, 2, 3, and 5 are all prime numbers, and that is the prime factorization of 60. 2 times 2 times 3 times 5 is the unique prime factorization of 60. So you can use that technique whenever you're trying to find the prime factorization. Okay, let's move on to the next level. Find the greatest common factor of the following pairs of algebraic expressions. Okay, find the greatest common factor of 45a to the second b to the third and 18a to the fourth b. Well, first we focus on the numerical coefficients, 45 and 18. The greatest common factor of 45 and 18 is 9. 9 times 5 is 45, and 9 times 2 is 18. So the greatest common factor will have a factor of 9 in it. Then we compare the variable parts, a to the second and a to the fourth. Well, the variable parts are they're pretty closely related to the prime factorization. A to the second is a times a, and a to the fourth is a times a times a times a. So common to both terms is the factor a to the second. So the greatest common factor will have a to the second. And then the other variable, the term on the left has b to the third, b times b times b. The term on the right has b. So one factor of b is common to both. So we end up with the greatest common factor of those two terms as 9a to the second b. Okay, the next pair, find the greatest common factor of 21m to the fifth n to the second and 28m to the fourth n to the second. First begin with the numerical factors, also called the coefficients. So 21 and 28, the greatest common factor of 21 and 28. Seven. Okay, 7 is a common factor to both terms. Now we look at the variable parts. The term on the left has m to the fifth. The term on the right has m to the fourth. So common to both is m to the fourth. And then both terms have n to the second. So common to both is n to the second. So the greatest common factor is 7 times m to the fourth times n to the second. Okay, now we're ready to start factoring. So remember the first sentence today? Factoring is the reverse process of multiplying. So in my opinion, one key to learning how to factor effectively is to first know how to multiply, because factoring is just the reverse process of multiplying. Okay, so down here, we're going to start factoring polynomials. And the first step in factoring is to factor out the greatest common factor of all the terms. So this is one of those statements you'll hear me repeat over and over again. The first step in factoring is to factor out the greatest common factor of all the terms. If it turns out that the greatest common factor is 1, then you proceed to the next step. Okay, factor the following expressions. We're beginning with a product that is, we're beginning with the result of what you get when you multiply. So the first thing we're going to do, we're going to identify the greatest common factor of the two terms. And then I'll show you how to factor that out. So first, look at the numerical factors, or the numerical coefficients, 28 and 24. The greatest common factor of 28 and 24 is 4. Then we compare the variable parts, a to the 5th compared with a to the 3rd. So a to the 3rd is common to both. And that's it. The term on the left has b to the 3rd, but the term on the right doesn't have any factors of b. So the greatest common factor is 4a to the 3rd. Okay, so think of the distributive property in reverse. So outside of the parentheses, we're going to write 4a to the 3rd. And inside the parentheses will go the expression that we need in order to get 28a to the 5th b to the 3rd plus 24a to the 3rd after multiplying 4a to the 3rd times whatever goes inside this set of parentheses. Well, since I'm factoring out a term with a positive coefficient, the plus sign is going to stay in the middle. And how do we know what term goes on the left? We can determine that if we divide 28a to the 5th b to the 3rd by 4a to the 3rd. So 28 divided by 4 is 7. A to the 5th divided by a to the 3rd is a to the 2nd. And then we still have b to the 3rd. So the first term inside the parentheses is 7a to the 2nd, b to the 3rd. To find the second term inside the parentheses, this time we're going to divide 24a to the 3rd by the greatest common factor. So 24a to the 3rd divided by 4a to the 3rd. 24 divided by 4 is 6. A to the 3rd divided by a to the 3rd is 1. So 6 is what goes on the inside. Okay, and we're done. This is the factorization of that expression. It's the reverse process of multiplying. Okay, and we can check our factoring by multiplying. So to check, we just apply the distributive property of multiplication over addition. So first we multiply 4a to the third times 7a to the second b to the third, and then plus 4a to the third times 6. And we can verify just by looking. 4 times 7 is 28. A to the third times a to the second is a to the fifth, and times b to the third. So that one checks out. And then the other one, 4a to the third times 6. 4 times 6 is 24. So we get 24a to the third, 24a to the third, which is the second term. Okay, so that means this is our factorization. Okay, let's look at the next example. This time we have 3 terms in a polynomial, and we want to factor it. So the first step in factoring is to factor out the greatest common factor. Okay, so we're comparing 3 terms. So first, the greatest common factor of the numerical factors, the greatest common factor of 25, 45, and 45. Yeah, it's 5. So we have a factor of 5. Then compare the variable parts. The first term has m to the 5th. The second term has m to the 3rd, and the third term has n. So common to all 3 is just m. So the greatest common factor has a factor of m. And even though the second and third terms have n and n to the 7th respectively, the first term doesn't have any factors of n. So the greatest common factor is 5m. Okay, so when we factor that out, we write 5m times the quantity. So inside the parentheses, the term on the left is what we get when we divide 25m to the 5th by 5m. So let's do the work over here. 25m to the 5th divided by the greatest common factor of 5m. That simplifies to 5m to the 4th. So the first term inside the parentheses is 5m to the 4th. As you are in the process of factoring, you can check your work visually along the way. So we can just look and see, is it the case that 5m times 5m to the 4th is 25m to the 5th? Well, that certainly seems to be the case because 5 times 5 is 25, and m times m to the 4th is m to the 5th. Okay, for the middle term, since we have subtraction, we'll write down a minus sign. And how do we know what we're going to subtract inside the parentheses? Well, we just divide 45m to the 3rd n by 5m. 45 divided by 5 is 9. M to the third divided by M is M to the second. And N divided by 1 is N. So inside the parentheses, the middle term is minus 9M to the second N. And once again, you can visually check that we're factoring correctly. So minus 5 times 9 is minus 45. M times M to the second is M to the third. And 1 times N is N. And then finally, the third term, since we have subtraction, we put a minus sign. So to find the third term inside the parentheses, this time we divide 45M times N to the seventh by 5M. And we get 9. 45 divided by 5 is 9. M divided by M is 1. And then N to the seventh. So inside the parentheses, the third term is minus 9 times N to the seventh. So that is the complete factorization. Hey, let's move on to the next page. Factor the following expressions continued. Here are a couple of cases where we, after finding the greatest common factor, even though it's not required, in my opinion, it will be more efficient to factor out the negative of the greatest common factor, because we have negative 42n to the third for the leading term. So let's first find the greatest common factor. And when we're doing this, we can just momentarily ignore the negatives. Just think of what you would do if you wanted to find the greatest common factor of 42 and 30. So what is the greatest common factor of 42 and 30? Well, let's jot down the prime factorizations of 42 and then 30. You can do it this way. 2 is a prime number and 2 is a factor of 42. So let's write down 2. We know that 2 times 21 is 42. 21 is 3 times 7, and both of those are prime numbers. So the prime factorization of 42 is 2 times 3 times 7. And then the prime factorization of 30. 30 is an even number, so 2 is a prime factor. 2 times 15 is 30. 15 is 3 times 5. And so common to both is 2 times 3, or 6. So the greatest common factor of the coefficients is 6. And then the variable parts, n to the third and n, the greatest common factor is n. Okay, so since the first term on the left, also called the leading term, since it has a negative coefficient, I tend to factor out the negative of the greatest common factor, factor out negative 6n. And then negative 42 n to the third divided by negative 6n is positive 7n to the second. And you can check by multiplying that you're factoring correctly. Negative 6n times 7n to the second is negative 42n to the third. Okay, then the next term inside the parentheses, well, think about negative 30n divided by negative 6n. Negative 30 divided by negative 6 is positive 5, and n divided by n is 1. So we're just left with this factorization, negative 6n times the quantity 7n to the second plus 5. Okay, the next expression, negative 14 t to the fifth minus 44 t to the fourth. The greatest common factor of 14 and 44. What's the greatest common factor of 14 and 44? The prime factorization of 14 is just 2 times 7. And the prime factorization of 44 is 2 times 2 times 11. So the greatest common factor is 2. Then when we compare the variable parts, t to the fifth and t to the fourth, t to the fourth is common to both. So since the leading term is negative 14 t to the fifth, I want to factor out negative 2 t to the fourth. And then in the parentheses, inside the parentheses, the first term is negative 14 t to the fifth divided by negative 2 t to the fourth. Negative 14 divided by negative 2 is positive 7. T to the fifth divided by t to the fourth is t. And then check, negative 2t to the fourth times 7t. Negative 2 times 7 is negative 14, and t to the fourth times t is t to the fifth, so that checks out. And then the next term inside the parentheses, divide negative 44 t to the fourth by negative 2 t to the fourth. Negative 44 divided by negative 2 is positive. I said that wrong. Negative 44 divided by negative 2 is positive 22. And t to the fourth divided by t to the fourth is 1. So this is our complete factorization. Okay, the next exercise, we want to learn a technique that we can sometimes apply when we are trying to factor a quadrinomial or a polynomial with 4 terms. So the 4 examples that follow are all quadrinomials. So once again, that means a polynomial with 4 terms. It's not always the case, but sometimes when you have a quadrinomial, you can factor by grouping. Okay, remember the first step in factoring. If the greatest common factor of all 4 terms is something other than 1, you want to factor that out first. But 1 is the greatest common factor of all 4 terms. So when we factor by grouping, we group the first and second terms. So we're focused on u to the second minus 9u, and we're going to factor that by factoring out the greatest common factor of just the first 2 terms. The greatest common factor of u to the second and minus 9u is u. So we factor u out, and we get u times the quantity u minus 9. When factoring by grouping, after we factor the first and second terms by factoring out the greatest common factor, this is an important step. Bring down the middle operator of the quadrinomial. The middle operator is subtraction. And what this is going to remind us of is that we're going to factor out the negative of the greatest common factor of the third and fourth terms. So the third and fourth terms, minus 2u and positive 18, the greatest common factor is 2. So we write minus 2. And what we're really doing is we're factoring out negative 2 from negative 2u plus 18. So negative 2u divided by negative 2 is u, and 18 divided by negative 2 is negative 9. Okay, so notice that we have a match in binomials. In the left, in this partial factoring, we have a binomial of u minus 9, and in the right, we have the same binomial u minus 9. So when factoring by grouping, this indicates that we can continue the factoring. In other words, the factoring by grouping will be successful when the 2 binomials match. So the next step is to factor out the binomial u minus 9 from each of those 2 products. So when we factor u minus 9 out of u times u minus 9, we get u minus 9 and then times the quantity. Well, we're factoring u minus 9 out, we're left with u on the inside. And then we factor u minus 9 out of the product on the right. So when we factor u minus 9 out of that, we're left with minus 2. Okay, so this is the complete factorization of the quadrinomial. Yesterday we reviewed multiplying, so you can always check by multiplying. Okay, so let's do that. Let's multiply u minus 9 times u minus 2. So u times u is u to the second, and then minus u times 2 is minus 2u. And then minus 9 times u is minus 9 times u. And then negative 9 times negative 2 is positive 18. It turns out we can simplify this, but we're just checking to see if it's equivalent to what we began with. The only difference is that the second and third terms are in different order, but those are equivalent. So this verifies that we factored correctly. Okay, let's look at the next example, factor by grouping. Out of the first and second terms, AB minus 2B, the greatest common factor is B. And when we factor B out of those terms, we're left with A minus 2. The next step in factoring by grouping, bring down the middle operator, subtraction. The greatest common factor of A and 2 is 1, so we're going to factor out negative 1. Negative A divided by negative 1 is A, positive A. 2 divided by negative 1 is negative 2. So we have a match in binomials A minus 2, so that means we can proceed. The next step, factor A minus 2 out of the two terms, and we're left with A minus 2 times B minus 1. Okay, the next example, q to the second minus 2q plus 6q minus 12. We're factoring by grouping, so out of the first two terms, q to the second minus 2q, the greatest common factor is q. So we factor q out, and then inside the parentheses, we're left with q minus 2. This time the middle operator is addition, so bring down the middle operator of addition. And then now we focus on the third and fourth terms. The greatest common factor of 6q and negative 12 is 6. So we factor 6 out, and we multiply 6 times the quantity q minus 2. The two binomials match. Q minus 2 over here and q minus 2 over there. So we can continue the factoring, factor out q minus 2. The other binomial is q plus 6. Okay, the next example, the third term should have a capital X instead of a lowercase x. So that was just a typographical error. But we want to factor by grouping if possible. So out of the first two terms, x squared minus 6x, the greatest common factor is x. So we factor x out of the first two terms. The binomial is x minus 6. The middle operator of the quadrinomial is addition, so we bring down addition. The greatest common factor of the third and fourth terms, 3x minus 18, the greatest common factor is 3. So we factor 3 out of the third and fourth terms. And the binomial is x minus 6. Okay, the two binomials match, x minus 6 in both places. So that means we can proceed. Now we factor x minus 6 out of both. And the second binomial is x plus 3. Okay, the next page, factor the following expressions. So this one just has two terms in it, so we're just going to factor the greatest common factor out of each of the two terms. So comparing negative 32 and 14, the greatest common factor is 2. If you want to factor out 2 or negative 2, it's okay. I'll just factor out positive 2 in this one. Then we compare the variable parts, m to the fourth and m. Common to both is one factor of m. And then the term on the left has n to the second. The term on the right has n to the third. Common to both is n to the second. So that's the greatest common factor, 2m times n to the second. And then we need to find what goes on the inside of the parentheses. So we can do that visually. Negative 32 divided by 2 is negative 16. M to the fourth divided by m is m to the third. And n to the second divided by n to the second is 1. Okay, then we move over to the next term. 14 divided by 2 is 7. M divided by m is 1. And n to the third divided by n to the second is n. So this is our factorization. Okay, the next expression, I believe there's a typographical error on this one. So let's skip that one for now. Let's move on to the next one. This one we have 3 terms. So we want to find the greatest common factor of all 3 terms. So when we compare the numerical coefficients, 30, negative 24, and negative 12. So what's the greatest common factor of 30, 24, and 12? So it looks like 6. 6 is the greatest common factor of 30, 24, and 12. And then the greatest common factor of m to the fifth, m to the third, and m to the second is m to the second. So we'll factor 6m to the second out. And inside the parentheses, the first term on the left, 30 divided by 6 is 5. M to the fifth divided by m to the second is m to the third. And then you can check by multiplying. 6m to the second times 5m to the third is 30m to the fifth. And then the middle term inside the parentheses, negative 24 divided by 6 is negative 4. M to the third divided by m to the second is m. And then the third term, negative 12 divided by 6 is negative 2. And m to the second divided by m to the second is 1. So this is our factorization. Hey, we can start the next bunch. Here we're factoring by grouping again. We have a quadrinomial. And so out of the first 2 terms, mn plus 7n, the greatest common factor is n. So we factor n out of the first 2 terms, and we're left with m plus 7 inside the parentheses. The middle operator is subtraction, so we bring down subtraction. The greatest common factor of negative m and negative 7 is positive 1. So we're going to factor out negative 1. And what goes inside the parentheses, Well, negative m divided by negative 1 is positive m. And then negative 7 divided by negative 1 is positive 7. So we have the binomial m plus 7. And since the binomials match, we can continue the factoring by factoring out m plus 7. And the other binomial is n minus 1. Hey, we can probably start the next one. Here we have a quadrinomial factor by grouping. Out of the first two terms, c to the second plus 3c, the greatest common factor is c, and the binomial that stays behind is c plus 3. Bring down the middle operator of addition. The greatest common factor of 2c and 6 is 2. Factor out 2, and we're left with the binomial c plus 3. The binomials match. That means we can continue the process, and when we factor c plus 3 out, the other binomial is c plus 2. Okay, we're out of time, so go ahead and sign in for attendance.
Are they never, like, is there ever a situation where they don't match up?
What's that?
Is there ever a situation like where these don't match up?
Yeah, you can, it's not too hard to create a quadrinomial that cannot be factored by grouping. But the reason that we're practicing it is because of another technique of factoring that incorporates the factoring by grouping.
I just figured I'd ask. I just figured I'd ask. I was like,